Hello, we are looking at an introduction to limits. This is from section 2.2 of your textbook. You can find this blank limit template if you'd like to copy along as we go on Blackboard. What we have on this first diagram are three pictures that look pretty similar. You can see there's a little bit of a difference here and here compared to the first picture. And so we'll be talking in this set a little bit about what limits are as a concept by looking at them from this graphical perspective. Two things we'll be thinking about is the function's value. Think of that as the actual output values at any particular input. And we'll be talking about what it means to have a limit, where a limit will be related to values, but not necessarily exactly the same. Let's take a look. In the first picture, we have what we can consider just an ordinary line. And we're going to be focusing our attention right here where x equals 8. So I'm going to assume that the function's name is f, and we can describe the point value of the function when the input is 8, the output is 1, and we can describe that with this language. F of 8 is equal to 1. I'm going to go ahead and jump over to the next picture and describe this one as a line with a hole. And so when we want to talk about the same thing, what's happening on the graph when x is 8, we can see that the function doesn't have a point value there. We say f of 8 is undefined. And if we move to the third picture, we're going to refer to this one as a line with, it has a hole, but there's a point, it's just been moved. So let's call it a line with a displaced point. And in this case, to find out if the function is defined, we're simply asking whether there is a point whose input coordinate is 8. And we can see that there is such a point, and that point is here. 1, 2, 3, 4 units high. So f of 8 is 4 for the third figure. Now, when it comes to the limit, we're going to use the notation, the limit of a function. Oops, that should say f of x. And right down below it, we'll put this little expression to tell you what input value we're considering. The limit of the function as x approaches 8. And so in this instance, we're going to be looking not at the point itself, but at the values approaching that point. And we're looking to see as we move along the graph, is there a predictable trend in the movement of the graph? And we can see that as the graph moves closer to where x is 8, the y coordinates are getting closer to 1. In the second picture, in the same way, if we move along the graph closer and closer to where x is 8, we can describe the limit as x approaches 8 of the function. And even though there's a hole there, the values are still getting closer and closer to 1. In our last case, we've got this point that's displaced, but we're still looking at the behavior as we move along the graph toward where x is 8. And in the same way, the limit of the function as x approaches 8. Doesn't matter that the point is here, that's not where these other values are headed. They're heading towards 1. So the first takeaway here is even though the pictures are differing slightly, the limit describes the same behavior because we're ultimately looking at the values approaching that point and not what happens when we actually get to where x equals 8. That's our first takeaway for limits. We're going to wrap that up this way. Notice the only place where these answers to the top row and the bottom row were the same was in this first example. And that's because there's no hole. So we're going to describe this key concept this way. If the graph is continuous, now that's an important word. We'll keep coming back to it. For now, we're going to use this as an easy way to think about continuity. For now, let's just say we think of continuous as basically meaning a graph that's unbroken. So if a graph is continuous, then the limit at a point is equal to the function value at that point. So we can apply this information about limits as essentially a conceptual shortcut. These problems ask you to evaluate a limit, but it also tells us that these are continuous functions. So we can use our key concept to say, if these functions are continuous, then the limit is the same as the function's value. So for each instance, because we know these are continuous, we just need to take this input value, plug it into the function expression, and calculate the output value. And that function value is the same as the limit value. So for number 1, we have, oops, I didn't leave much space, 3 times 4 squared plus 5 times 4 minus 2. And if we work through the calculation on that, we'll get 66. You'll see these other ones worked out in the answer key posted to Blackboard. You'll have a chance to look at some problems like these in class coming up, so I'll leave those ones blank for now, but since they're continuous functions, they would work in just the same way. So let's talk about the direct substitution rule. The direct substitution rule is essentially a summary statement of what we've just been doing in these 4 exercises. Let's write it this way. If A is in the domain of our function f, then the limit as x approaches a of f of x is equal to f of a. Now we need to make 2 remarks about this expression. Number 1, the direct substitution rule only works if our function f is continuous. Later on in the course, maybe next week or later this week, we'll talk about what do we do if a function's not continuous. If it has a hole or some other kind of a break, then how do we evaluate a limit? But for now, we're starting with continuous functions, and we've got the substitution rule. And just to put that in simple terms, our first step is to plug in the value. Let's say plug it in. And by plug it, I'm talking about the input value that's specified for us. All right, let's look at another example. Here we have a new limit problem. And if we try our direct substitution rule, plug it in, when we plug in, what happens? Plugging in 1 gives us 3 times 1 squared minus 8 times 1 plus 5. That's a value of 0. And in the denominator, we also get a value of 0. Now that's not an answer. We can't divide by 0. That's an undefined operation. So in this instance, plugging it in did not give us a result. That's actually our first key that this is an example that's not a continuous function. So let's jot down a key fact over here. 0 over 0 is an inconclusive result. So what are we going to do if we get an inconclusive result? We need to use some other strategies. For now, we're going to limit those strategies to graphs or algebra. We'll get back into the details.